Good morning, pre-calculus. Right, today we're going to continue looking at our trigonometry. We're going to look at the trigonometry functions, right triangle trigonometric functions. All right, and as we look at, we call it right triangle trigonometry. Because right now, we're going to limit ourselves to just what is happening in nice, well-behaved right triangles. And in a right triangle, I'm going to have a reference angle. I'm going to call it theta. So if I call this angle my theta, my unknown angle, then I can have show a relationship between the angle and the sides. I need to state the different sides. We know Pythagorean theorem says leg squared plus leg squared equals hypotenuse squared. But in Pythagorean theorem, it doesn't matter which way you put the legs in. We also know that the angles inside of a triangle add up to 180. So if that's 90, those two would have to be complementary. But neither one of those things shows a relationship between the side lengths and the actual angle measures. In order to do that, we're going to take a closer look. So this side over here is opposite from the angle, so we call it the opposite side. This is the hypotenuse. And this side is adjacent to the angle, so we call it the adjacent side. So everything's based on the reference angle. If we change the reference angle, if I change my reference angle to here, the hypotenuse would still be the hypotenuse, but now the adjacent side is opposite, and the opposite side is now adjacent when I change the reference angle. We have 6 trigonometric functions. I'd like to take a look at all 6 of the trigonometric functions right now. The first one is called sine, S-I-N-E. We usually just abbreviate that as S-I-N, but we would still say sine, we don't say sin. And the sine of any angle is the ratio of the opposite side divided by the hypotenuse. So the sine function, the sine of that angle, is the same as however long this side is divided by that side there. There's the relationship between an angle and the side lengths. The next trigonometric function is cosine. We usually abbreviate that as COS. And the cosine of any angle is the ratio of the adjacent side divided by the hypotenuse. The next one is tangent, abbreviated as TAN. And the tangent of any angle is given as the opposite side divided by the adjacent side. Next we have cotangent, abbreviated as COT. And the cotangent of any angle is the inverse of the tangent. So it would be the adjacent divided by opposite. And then we have the secant, abbreviated SEC. The secant of any angle is the ratio of the hypotenuse divided by the adjacent. And then finally the cosecant, abbreviated as CSC. And the cosecant ratio is the hypotenuse divided by the opposite side. So here they are, all 6 trigonometric functions. We should probably remember some of these from previous class. We might remember the mnemonic device SOHCAHTOA. SOHCAHTOA. And this tells me that the sine ratio is opposite over hypotenuse, cosine ratio is adjacent over hypotenuse, and the tangent ratio is opposite over adjacent. But what about these other ones, cotangent, secant, and cosecant? There is a relationship here, and I want you to take a look at this. If I compare tangent and cotangent, tangent is opposite over adjacent, cotangent is adjacent over opposite. They're inverses. Same thing with cosine and secant. The cosine is adjacent over hypotenuse, the secant is hypotenuse over adjacent. And finally, sine and cosecant. Sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite. So when you know the first three, you know them all. When working with the trigonometric ratios, there are two very important triangles. You saw these triangles in geometry. You used them for a couple of things, but not for much. And I want to take a closer look at them. So these are special triangles. There's two of them. The first one is called the 45-45-90 triangle because, rather unimaginatively, those are the angles inside of the triangle. 45 degrees and 45 degrees. We also know that this is going to be an isosceles triangle. And one of the properties of isosceles triangle is if the base angles are congruent, that means the side lengths are also going to be congruent. And as I take a look at this, and I think of, well, what if I call each of these lengths 1 and 1? How long would the hypotenuse be? Using Pythagorean theorem, we can quickly find that the hypotenuse would be the square root of 2. Now, what's the significance of this special right triangle? It's going to allow me to do some trig in my head. For example, if I asked you, well, what's the sine of 45 degrees? We know that the sine ratio is opposite over hypotenuse. Here's the 45, opposite over hypotenuse, 1 over root 2. Now, of course, we want to rationalize the denominator there, so multiply by root 2 over root 2, and I get root 2 over 2. How about the cosine of 45 degrees? Cosine is adjacent over hypotenuse, 1 over root 2. Again, rationalize the denominator, root 2 over 2. Tangent of 45 degrees. The tangent ratio is opposite over adjacent, 1 over 1, so it would just be 1. The cotangent of 45 degrees would be adjacent over opposite, the inverse of this, 1 over 1, it's 1. The secant of 45 degrees. The secant of 45 degrees is going to be hypotenuse over adjacent. It's going to be root 2 over 1, which is root 2. And then finally, the cosecant of 45 degrees is going to be the hypotenuse over opposite, root 2 over 1, which is root 2. So we're finding exact values here. I want to compare this to what we see on the calculator, so I'm going to turn on my calculator here. I'm going to make sure I'm in degree mode. This is going to be an issue. Whenever we're working with trig on our calculators, you got to know what mode you're in. Since all of these are in degree mode, I want to make sure I'm in degree mode. So I'm going to go down to the mode and change it to degree mode, and then exit out of there. If I do the cosine of 45, cosine of 45 is 0.707106781 approximately. Now, if I do this calculation here, the square root of 2 divided by 2, it's the same thing. This is the exact value. That's a decimal approximation. So the 45-45-90 triangle gives us all of the trigonometric functions, sine, cosine, tangent, cotangent, secant, cosecant for 45 degrees. Let's take a look at the other special right triangle. Again, I'm moving a little fast here. You can rewatch this video if you didn't get all of this down, and you can kind of pause it and go over these and make sure you've got all these numbers down. The next special right triangle is the 30-60-90. Again, because rather unimaginatively, those are the angles involved in the triangle. I'm trying to draw this one to scale so that this is a 60-degree angle and a 30-degree angle. This triangle, the 45-45-90 is half of a perfect square. This one comes from a perfect triangle, where if I had the other side of this, I would have 60-60-60, an equilateral equal angular triangle where all the sides would be the same. which means that this side would be twice as long as this side. So if I say this is 1 and this is 2, again, think about it as a full equilateral triangle where all of the sides are 2. Half of it would be 1. The missing side here, using a Pythagorean theorem, 4 minus 1 would be root 3. Now, can you see how I'm going to be able to get the trigonometric functions of the 30 degrees and the 60 degrees? Let's take a look at this. So let's do 60 degrees first. If I want to do the sine of 60 degrees, sine is opposite over hypotenuse. It's going to be root 3 over 2. The cosine of 60 degrees is going to be adjacent over hypotenuse, 1/2. The tangent of 60 degrees is going to be opposite over adjacent, root 3 over 1, which is just root 3. The cotangent of 60 degrees, and we can start thinking of these as inverses. It's going to be the inverse of this. 1 over root 3, rationalize the denominator, root 3 over 3. The secant of 60 degrees is going to be the inverse of cosine, so 2 over 1, which is just 2. And then the cosecant of 60 degrees is going to be the inverse of sine, 2 over root 3, rationalize the denominator, multiply by root 3 over root 3, and I get 2 root 3 over 3. I can do the same thing with 30 degrees. So looking here, 60, when my reference angle is 60 degrees, my opposite is root 3, my adjacent is 1, the hypotenuse is 2. If I change the reference angle to 30 degrees, and I say, well, what's the sine of 30 degrees? I'm changing these. So sine is still opposite over hypotenuse, but now the 1 is opposite from 30 degrees. So opposite over hypotenuse is going to be 1/2. The cosine of 30 degrees will be the adjacent over hypotenuse, root 3 over 2. The tangent of 30 degrees will be opposite over adjacent, 1 over root 3. Rationalize the denominator, multiply by root 3 over root 3, and I get root 3 over 3. The cotangent of 30 degrees, and now I think we can use our shortcuts. It's just this one flipped. So root 3 over 1, which is just root 3. The secant of 30 degrees is going to be the reciprocal of cosine, 2 over root 3. Rationalize the denominator, 2 root 3 over 3. And then finally, the cosecant of 30 degrees is going to be 2 over 1, which is just 2. Again, I want to look on the calculator and take a look at what the calculator says about these. So if I take, let's take a look at cotangent of, or let's look at the tangent of 30, and then we'll talk about how to do cotangent. So if I do the tangent of 30 degrees equals, there it is, 0.5777. Now I'm going to do this calculation. The square root of 3 divided by 3. And it's the same thing. So sine, cosine, and tangent are pretty obvious. But how would I do something like the cotangent? Let's take a look at that for a moment. Suppose I want to find what is the cotangent of 60 degrees. Now, we already did it on the previous problem. I know that it's root 3 over 3. But how would I do this on the calculator? Well, the reciprocal functions. Cotangent is the same thing as 1 over tangent of 60 degrees. So cotangent, I can plug it in my calculator like this. 1 divided by tangent of 60. Because 1 over the tangent is the cotangent. It equals, there it is, the same thing as we did before, square root of 3 over 3, and it's the same. What else can we do? We can think about these angles also as radian measures. For example, if I want to convert let's convert 30 degrees, so 30 degrees to radians. All right, so 30 degrees times pi over 180 degrees. and the degrees are going to cancel. 3 over 18, we should know that that is pi over 6 radians. Now earlier we saw that the sine of 30 is 1/2. We know that the sine of 30 degrees is 1/2. What about the sine of pi over 6? This is where you have to make sure you're in the right degree mode. So I'm going to hit the mode button. This is a radian, so I need to be in radian mode. Exit out of there. Now I'm going to do sine of pi over 6. 0.5, 1/2. There it is. So knowing the angles in degrees, we know the angles in radians, being able to switch back and forth, and finding the sine, cosine, and tangent of all of our reference angles. I want to do one more sample problem. What if it's not such a nice angle? Not one of our reference angles. For example, what if I had a triangle that looked like this? And this side is 8, and this side is 5. And here's my reference angle right there. And I want to find the sine of the angle, cosine, tangent, cotangent, secant, and cosecant of that angle. Well, sine is easy. The sine is going to be opposite over hypotenuse, 5/8. But the cosine is adjacent over hypotenuse, something over 8, but I don't know what it is. I need to find this missing side. So the problem comes to a screeching halt here, and I need to go find that missing side. I need to find this side right here. I'll call it x. Well, Pythagorean theorem, a squared plus b squared equals c squared, x squared plus 5 squared equals 8 squared, x squared plus 25 equals 64. Subtract 25 from both sides. 65, 55, 45, and I get 39. So x equals the square root of 39. 3 times 13, we can't even simplify. Can't do anything with that. But that's the missing side, the square root of 39. So that is what's going to go here, the square root of 39. The adjacent over the hypotenuse. All right, so let's finish it out. Tangent is going to be opposite over adjacent, which is going to be 5 over the square root of 39. Rationalize the denominator, multiply by root 39 over root 39, and I get 5 root 39 over 39. And then I'll leave you to finish it and do the cotangent, secant, and cosecant. And of course the cosecant is going to be 8 over 5. The secant is going to be 8 over root 39, rationalize the denominator. And the cotangent is going to be, flip this, root 39 over 5. So sometimes we might not have all of the information. We have to use Pythagorean theorem to find a missing side. All right, so we're going to hit pause on the lesson right here. If you want to take a look at the first few problems in the homework, or if you just want to jump right onto the second part of the lesson, it's up to you. And I'll be back in a moment.